Now that we have explained how the temperature changes depending on the distance from the Earth, we're going to discuss now about temperature variations over a longer period of time. So what is called long-term variations in average temperature, which is the single most important attribute of climate change. So this is the one that actually is telling us that there is a change of climate that is unusual and is not dependent on the natural phenomena that can occur. So probably you have seen already one of the figures where you can see temperature variations along thousands of years, right? And I'm just going to quickly explain or quickly remind you how these climatologists have used a number of clues to understand how global temperatures have varied, or how a way to measure this. So the evidence has been gathered from historical documents, but they cannot go that far, but they can go very far by measuring the rings on trees. And then there are some other things like fossil pollen analysis, etc. But two of the most important measurements that have allowed us to understand temperature variations, long-term variations, are the measurement of the ice cores and seafloor sediments. To be more precise, isotopes of hydrogen and oxygen on these materials. And briefly, I'm just going to explain how it works. And basically, we have different stable isotopes and also unstable isotopes in each element. And some stable isotopes can actually tell us geological time and actually can tell us about events. In the molecule of water, we can have isotopes from the hydrogen and isotopes from the oxygen. So we can call them some heavy isotopes and light isotopes because of the atomic number. So we have, instead of hydrogen 1, which is the atomic number that we use commonly for conventionally when we're talking about elements and compounds, chemical composition, we can have isotope 2, which is known to be heavier, right? And for the oxygen, which the atomic number is 16, we have the heaviest one being 18, right? So these isotopes, actually, since they are heavier, they will tend to evaporate less in the ocean, and therefore we will find them less commonly on the Antarctic ice, on the Arctic and Antarctic ice, right? So this has allowed, it also depends on the temperature. So this has allowed scientists to measure whether there were warming periods or cold periods in the Earth by measuring the amount of isotopes present, heavier and light isotopes, in this ice core or these sediments. And sediments will be the opposite, because we're talking about sea sediments that are storage in heavy isotopes and light isotopes upon the changes in temperature, right? So they have taken samples in Greenland and Antarctic that provide really a picture of the climate and also the composition of the Earth's atmosphere over hundreds of thousands of years of history. So it provides the temperature record, the isotope analysis, and then the analysis of the air bubbles capturing the ice correspond to the concentrations of variations of atmospheric gases, as well as wind-blown dust and ash. So this is very important, and this is key that has allowed us to understand what were the conditions, the atmospheric conditions and the temperature conditions over more than 100,000 years. So so we have, I'm showing you now this very nice picture about the cycles. And this one and so this variation, now we know, is clear that we have oscillations, we can see, and we can even identify some glacial periods, right? So over during the glacial periods, the greenhouse gases CO2 and CH4 are low, and during warmer interglacial periods they are high. So this figure shows the Antarctic carbon dioxide and methane concentrations, and over more than 600,000 years, right? And you can see the strong correlation that they both have in terms of the oscillations, right? So it shows a strong correlation, also matching glacial periods, for example. So during glacial periods, the greenhouse gases, both CO2 and methane, are low, and during the warmer interglacial periods they are high. So perhaps the most startling feature in the figure is how much higher the current CO2 concentrations is than it has been in over 650,000 years, right? But what is really not clear by looking at only this figure is whether it is changing concentrations of greenhouses that cause temperature changes or vice versa. So switches from glacial to interglacial periods may well be triggered by other phenomena. And this other phenomena is the one that we are going to explain now, that is the orbital variations on the Earth. This could have actually caused the variations of these gases. So we're going to explain, and also it also explains very well the glacial periods. So to have a distinction between what is now human-induced climate change over the natural variations, we need to understand these natural variations. All right. So from these figures, we can see that there has been dramatic changes to our climate, right? And there has been some ice ages that have come and gone. But what is surprising is that there is a strong pattern that explains these ice ages. And I already told you about these natural things, natural phenomena that occur that explains this. So this is called the Milankovic Cycle. It was named after this scientist, that he explains how the Earth's climate changed over hundreds of thousands of years. And his theory is based on two key ideas. First, the Earth's climate is strongly affected by how much sunlight the northern latitudes receive during the summer. And second, this amount of sunlight varies based on changes in the Earth's orbit and rotation. So why are the northern latitudes so important? Can you think about why? Well, it's key. It's because of the ice. When sunlight hits the ground, most of the energy is absorbed as heat. But if the ground is covered in ice, most of the light reflects away because ice is white. And later on we will have the definition about the albedo definition, which actually tells us the percentage that, of how much is reflected of this sunlight, right? So this thing about reflection of the ice because of the color, it creates a positive feedback loop. So ice forms when it's cold, but ice also reflects light, so making it colder, which forms more ice. So it is called positive feedback loop because it tends to being reinforced. So ice is really important for climate. The northern and southern hemisphere both contains lots of ice, but there's more ice in the north because there's more land. And land has lower heat capacity than water, which means that water doesn't change temperature as easily as land does. This is why coastal regions are generally more mild and why ice forms more easily on land. So the key variable here is how much ice melts during the summer. So we have come up with two key things, right? That the ice the ice cover regulates the Earth's temperature, and also it depends on how much ice melts during the summer. And the Milankovic cycles explain this by telling you how far sometimes is the Earth from the sunlight during the summertime. So Milankovic showed that over hundreds of thousands of years, the amount of summer sunlight can shift plus or minus 15%, and this can bring ice ages. Imagine, this can end ice, and this can also finish ice ages. So there are three primary orbital cycles, and the shape of the Earth's orbit oscillates from elliptical to more nearly circular with a period of 100,000 years. And this movement, and this is called eccentricity. And then the Earth tilt angle with respect to its orbit fluctuates from 20.5 degrees to 24.5 degrees with a period of 41,000 years, and this is called obliquity. And currently the Earth's position is 23.5 degrees. Finally, then we have something, the orbit cycle that is called precession, and this is a period of 23,000 years, and this is a movement that occurs on the Earth's spin axis. So these three movements, variations, change the distance in summertime from the Earth to the Sun, and this affects the ice, the melting of the ice, or the possibility of having more ice in the poles. Well, it is also important to mention that the shapes of Earth's orbit is not totally elliptical. It is more like a circular shape. But even these small variations make a significant change on the amount of sunlight inciding the Earth. So we have explained that the sun and the orbital movements change the climate. We know that the changes are responsible for the comings and goings of the ice ages, but the warming that we've seen in the last few decades cannot be linked, therefore, to the Earth's orbit because it is too large to be caused by the solar activity. So this figure shows the total incoming solar radiation changes over time. And these changes of incoming solar radiation are mainly affected by the eccentricity. And eccentricity is a 100,000 year cycle, right? If you can see now, you can notice that the variations that we have in incoming solar radiation are within the range of 0.5 watts per square meter. So this range of variation cannot explain the increase and decrease in temperature variations, because if we will make the conversion of this solar incoming radiation to the degrees, to the change in temperature, that will be very, very small. Just let's keep in mind that the changes in global temperature from the records that we have up to the present have been varied no more than plus minus 5 to 6 degrees, right? But the incoming solar radiation also have another factor that affects it. So this factor is the variations in the intensity of radiation emitted from the sun itself. So, for example, the sun spins on its axis, making one complete rotation every 27 days. There are darker and brighter areas on the solar surface that cause variations of up to 0.2% in the total solar amount of radiation reaching the Earth over a 27-day period. So we have this 27-day period cycle, and then we have another important cycle. So the 27-day period occurs so rapidly that is not particularly important to determine average global climate. But then the other one of more significant importance is the 11-year cycle that I was talking about. So during peak periods of magnetic solar activity, the surface has large numbers of cooler, darker regions called sunspots. And these sunspots can block some solar radiation. But the key thing is that these sunspots are accompanied by other regions that are called faculae, and these are brighter than the surrounding surface. So the net effect of sunspots that dim the sun and faculae that brighten it is an increase in solar intensity during periods of increased number of sunspots. The variations in solar radiation reaching the Earth as a result of these cycles is roughly 0.1%, which is thought to be enough to change the Earth's temperature by 0.2 degrees Celsius. You can see the amount of sunspots in this figure and how this follows the 11-year cycle.